how did those researchers achieve the pulse measurement in this very tough situation? This is what they did. They used the so-called frog crab method. So for the time being, forget about the abbreviation. Okay, just look at what is the they used. So in this figure, you can see they just used the intense infrared driving pulse in both generation and the measurement. The red path means the infrared pulse. Focus the infrared pulse into the first gas jet, okay? And the light has to be very intense, to the order of 10 to the 14th watt per centimeter square, such that high harmonic generation, HHG, can occur. And it will generate broadband extreme ultraviolet, EUV. Okay? So at the output, you will see the blue path means EUV light. The red one means the original infrared. Okay. You have both. Then they use a filter placed here to select high frequency components. Okay? The bottom figure shows the EUV spectrum measured by a grating here and an EUV CCD. Okay? And you can see the spectrum exhibits two different regions. For low frequencies, you will see periodic structure. Okay? For high frequency, you see continuous spectrum. Okay? So they use the filter to select the high frequency part. Okay? So this is the continuous EUV spectrum selected by the filter. And what is the major difference between these two regions? If you have a periodic spectrum, what is the time domain characteristics? As you have studied, if you have a frequency domain comb, you will have a time domain comb simultaneously, right? So the low frequency part corresponds to periodic pulse trend in the time domain. But the high frequency part, because the spectrum is continuous, no periodic structure anymore, so this part corresponds to an isolated EUV pulse. That's the major difference. And in this experiment, they select the isolated part. Then they have to introduce optical delay between the infrared and the EUV. Okay, supposedly it's pretty trivial, right? In the infrared, you just need a beam splitter, you use some mirrors, you can create optical delay, such as standard microsecond interferometer. But in the EUV regime, it's very difficult to do that because the beam splitter for EUV is kind of rare. So this is what they did. They use a specific mirror. This is the side view, so you might not be able to identify the reality, but just imagine it's a concentric structure. The inner part, okay, which is shown here, can be driven by an actuator. Okay. The outer part, you can imagine it's a concentric ring, okay, will be relatively translated with respect to the central part. So if the EUV shines the central part and the infrared shine the outer rims, there will be a relative delay between them. Okay. So this is what they did. Instead of using a beam splitter, this is the way they create the delay for infrared and EUV pulses. Then focus infrared and the EUV onto the second gas jet. Okay, so it means some ionization will occur in the second gas jet. And then finally, they will measure the electron spectrum Be careful, this is not optical spectrum. EUV spectrum has been measured here. So this is something different. This is about electron spectrum. And measured by a TOF spectrometer. TOF means time of flight tube. Okay? So although it is used in measuring the spectrum, but apparently very different from this one. Grating CCD, that's the typical way you measure optical spectrum. But to measure electron spectrum, you need something different. TOF is what they use. So I need to introduce what is TOF. Okay? This is a magnet schematic diagram. South pole, north pole. So some magnetic field will be generated here. And you can see magnetic coil here and here. So like a solenoid, right? It will create some uniform magnetic field in between. And when your EUV drives the second gas jet, because of the high photon energy, some gas atom could be ionized, okay? Releasing some free electrons, right? So imagine initially maybe some electrons are released, but with certain initial velocity. But the electron is traveling in an environment full with magnetic field. So you know the Lorentz force equation, right? QU cross B means the Lorentz force the electron experienced. So basically, the electron will follow some spiral path traveling to the right and captured by MCP, multi-channel plate. You can imagine this is a two-dimensional array with many small pixels. Each small pixel can translate electron signal to some electric signal you can detect it outside. Okay, so whenever there is an ionized electron, free electron, it will be captured by some pixel on the MCP. Okay, but there are much more than one electron during ionization, right? There are a lot of different electrons, and each electron might have its own initial velocity. Okay. And now the TOF, the purpose of TOF is measuring the electron spectrum. 那什么叫做 electron spectrum 啊？就是不同的电子能量各占的多少，那个分布图叫做 electron spectrum. Okay. But how could the TOF spectrometer achieve this goal? They have to capture some statistic histogram. Okay, the horizontal axis is time of flight, TOF, right? So it means, in addition to knowing which pixel captures some electron, you have to record how long does the electron travel from the initial point to the MCP. So you have to record two things: which pixel and how long does it take. Okay. And the vertical axis means number of counts. Okay. So the longer the traveling time means what? Means the slower the initial velocity, right? 所以横轴越往右边花的时间越长，就对应什么？越低的电子初速度，也就是越低的电子动能。OK。所以横轴大致上就是 electron energy, but in reverse direction. Vertical axis proportional to the number of counts. It's proportional to the strength, right? The more the electron with certain velocity, the higher the number of counts you can record. So in this way, they can measure the electron spectrum with this TOF spectrometer. Then, what could they do? in this figure, we try to illustrate why the electron can reveal the information of actually both the infrared driving pulse as well as the EUV pulse. You can get two things at the end. Okay. So for imagine you have some EUV pulse here, but this EUV pulse comes from high harmonic generation in the presence of infrared driving pulse. So infrared field is plotted here with much longer wavelengths compared with EUV. Okay. So you within the first order, the EUV pulse will see something close to sinusoidal infrared electric field, and the electric field will modulate the EUV spectrum. Okay. So just like this case, the infrared field is here. The another curve means the corresponding phase modulation due to the presence of infrared electric field. So this EUV pulse will see a phase modulation curve with a positive slope. Okay, and according to the Fourier transform theory, we know if the after time derivative of your phase modulation in the time domain, it means a frequency shift in the frequency domain, right? So it means this EUV spectrum will be shifted because of the infrared driving field. Without the infrared, the EUV electron spectrum might be here. But because of infrared, it can be shifted to the lower or higher frequency components, depending on the sign of slope. Okay, positive slope or negative slope, the electron spectrum will be shifted downward or upward differently. Okay, so if you look at the spectrogram, this is the electron spectrogram. Horizontal axis is the delay, vertical axis is electron energy, okay, just like a frog trace. And if you look at here, you will see light blue, deep blue colors, right, alternating with delay. That means this thing happens. Your electron spectrum is shifted up and down periodically because of the periodic infrared driving field. Okay, so the intuitive idea is if you look at the variation of the electron spectrum, you can directly know the corresponding temporal phase modulation curve. Then you can know directly the driving electric field. So that's why you can get the infrared driving electric field from the electron spectrogram measurement. Okay, so that explains what they did to measure the light transient in the infrared. Something more is by processing this data set, two-dimensional data set, such very similar to the frog method. By interactive algorithm, eventually you can get not only the infrared driving field, but also the corresponding EUV pulse simultaneously. And this is in the order of attosecond regime. And in this specific example, the infrared is in the order of 2.1 femtosecond. Okay. So they are of different time scales. Okay. So overall, the frog crab method is very similar to the blind frog we introduced before, right? The difference is in the cross-correlation frog, maybe the reference pulse or gate pulse you have known. But in the blind frog, you don't know both either, right? And this is similar to the blind frog. Okay, so this is the first glance about how did the researchers achieve the measurement of attosecond EUV pulse as well as the infrared light transient simultaneously. you will see a very different experimental apparatus. You need 2 gas jets for high harmonic generation. You need time of flight spectrometer to measure the electrons spectrum. Okay, so pretty complicated. And besides, the driving field has to be very intense. Otherwise, no high harmonic generation can occur. So this method does not work when you have a very short light transient, but the intensity is low. Then this method does not work. Okay, I just show you the measurement results in the published paper. There are 6 cases in their measurement. The left column shows the electron spectrogram, 2-dimensional data trace. The central column shows the infrared electric field. So you will see positive and the negative values by using the method we just introduced. The right column shows the temporal intensity, so only positive numbers in the right column. So maybe just take absolute square. You can get the blue curves from the corresponding red curves. So what did they do? From figure A to figure C, the delay of visible to UV part varies in steps of 0.2 femtosecond or 1/4 of pi. Okay, so they just use these 3 figures to demonstrate the light transient or electric field can change with the change of delay. Okay, this is this is echoing what we discussed last time. We mentioned that in addition to individually compressed 3 spectral bands, it's insufficient, right? We need to control the relative delay. Furthermore, we need to control the CEP phase such that you can have unique electric field. So the first 3 figures demonstrated the importance of delay. Whenever you change the delay, even though the 3 individual bands correspond to the nearly transform limited pulse, no change. But the synthesized electric field changes, right? You can see very difference between these 3 cases. Figure D shows delays and the CEPs are tuned to have twin transients. So they purposely control the CEP and the delay such that you can have transient pulses， 就两团，就是他在 demo 说，我控制了 delay 跟 CEP， 即使3个 band 都差不多是完美的色散补偿，我还是可以合成出很不一样的 pulse， 比如说从 single pulse 变成 twin pulse。And figure F shows the highest energy concentration. Okay, the corresponding temporal intensity is here. So they have to tune different knobs with certain procedure. In the end, this is the best that they could achieve. What is the meaning of best? They try to concentrate as much energy as possible to the central main lobe. This is the best they could achieve. 35% energy is there. Okay, and it corresponds to 2.1 femtosecond light transient or 0.88 cycles. Okay, below single cycle, and that's why it's controversial. If you use the term of pulse, it's controversial, so they call it light transient. 所以最后这个就是所谓的2.1飞秒，是这个 case。它必须去找出适当的 CEP 跟适当的 delay 条件，所以有很多 control knobs 必须去 optimize。他没有细谈到底是要怎么 optimize， 不过他最后得到最好的 case 是这样。
How do CEPs affect your envelope shape?
Envelope. They have 3 CP control knobs, right? For each band, there is a CP control with a wedge pair. So the function of that wedge pair is controlling the relative timing between the envelope and the fringes. But you have 3 bands, so that means you have 3 relative timing between envelope and the fringes. And I think it's quite intuitive. If you control if you change the CP, the synthesized, the envelope will not change, but the positions of the fringes will change. And when the 3 electric fields synthesize together to get a single electric field, I think it's not surprising. When you change the CP, the synthesized electric field will change as well. But after the synthesize, the total envelope will change. 我想差别是这样，一个一个 band 来看 ，envelope 都没有办法因为 CP 而改变，但是 total 的 envelope 会因为这3个个别的 CP 而改变。Okay, so if you are interested, you can use a computer program to simulate the impact of CP. Just use 2 bands, you will see a very obvious impact. It's about the post-measurement method named Modified Interferometric Field Autocorrelation. Our acronym is MIFA or MIFA. To talk about the MIFA method, I will introduce second harmonic generation with thick crystal. Okay, and why using this kind of thick crystal you can have modified field autocorrelation function. Okay, you have studied field autocorrelation function before, right? In lesson 5, but this is something new. And introducing why if you measure 2 modified field autocorrelation functions, you can reconstruct the spectral phase function. And finally, some experimental results. So starting with second harmonic formalism, this is easy. If the light is continuous wave, the SHG is quite easy. Okay, A omega means the phasor of the CW fundamental light. So the electric field is phasor times e to the j omega t, and the second harmonic generation simply means square in the time domain. So you will have a second harmonic phasor, which is the square of fundamental phasor. Okay, and the carrier frequency is doubled. And if you work with short pulse, it's pretty similar, just square in the time domain, but this time instead of a constant phasor, you have a temporal envelope function, complex temporal envelope function. So that means your amplitude and the phase can be functions of time instead of constant. But it's still the same. So in second harmonic domain, the carrier frequency is still doubled, and the second harmonic temporal envelope function is the square of fundamental function. Okay. But how about the frequency domain picture? Okay. So if you look at the, this is your second harmonic temporal envelope. After Fourier transform, you got its spectral envelope, right? And the square means A omega times A omega itself. Okay. But in the frequency domain, it means the convolution between the individual Fourier transform. So big A omega convolves with big A of omega itself. It's autoconvolution relation. And if you substitute the convolution formula, this is what happens, right? Standard convolution formula in the frequency domain, okay? But we need some insight, interpret what is the meaning of the previous formula, okay? So imagine the red one is the fundamental spectrum, the blue one is the second harmonic spectrum, okay? So if you look at a single second harmonic frequency, say big omega 0, and about the contributions from the fundamental to this specific frequency component. The most intuitive idea is to generate big omega 0, you need two fundamental photons at omega 0 over 2, right? Then after second harmonic generation, this frequency component will contribute to this frequency component as a second harmonic band. It's intuitive, but it's not totally right. Because if you think about the convolution formula, it states that a single frequency component as a second harmonic band does not just come from a single fundamental frequency, but infinitely many combinations of fundamental frequencies. Okay? So let me show you several examples. For example, can be the some frequency generation between these two fundamental frequency components. One is omega prime, the other is omega 0 minus omega prime. And then after some frequency generation, they will contribute to second harmonic frequency at omega 0, right? Still. And you can further generalize to this combination. By changing omega prime, you can see a lot of, actually essentially all the fundamental frequency components will contribute to a single second harmonic frequency component, right? So this is the starting point of MIFA method. A single second harmonic frequency at big omega 0 results from the sum frequency generation, or SFG, of many fundamental frequency pairs at omega prime and omega 0 minus omega prime. So what does it mean? It means much information of the fundamental spectrum is encoded at a single second harmonic frequency component omega 0 alone. 所以直觉上来讲是，我如果想量这个 fundamental spectrum 的 information, of course, spectral phase is our interest, right? Maybe 我不需要去把整个 second harmonic 通通记下来，我单单取这一个 frequency component, maybe 就都在那里了。That's the original idea. Okay.